Hi, I'm Benny, and I've dedicated my life to understanding the universe, with the hope that one day I'll get the chance to hop on a rocket and see it for myself. Growing up, I was always looking up, not just at the stars, but at the endless questions they sparked. I'd spend hours wondering what was out there, how it all worked, and if I'd ever get the chance to see it for myself. This is Space Bites, where I take the overwhelming, mind bending world of space and break it down into small, easy to digest pieces. Think of it like snacking on the cosmos, quick, simple, and deliciously full of wonder, so anyone can understand and enjoy it no matter their background. Why? Because every atom in your body was forged in the heart of a star. The carbon in your DNA, the oxygen you breathe, the calcium in your bones, all of it began in stellar furnaces, which means, quite literally, the universe is in you. You are the product of cosmic alchemy billions of years in the making. The same processes that built galaxies also built you, linking your existence to the cosmos itself. If you're listening to this episode, then you might not know much about the underlying physics of the world around you. And so I want you to ask yourself this really simple question. What is this? What is this thing that you're sitting on right now? And what is the air that is moving in and out of your lungs? And what is this device that you're listening on? And what is your hand? And what are your thoughts? And what is any of it really at the most basic level? And I think if you're listening to this episode, then you're probably here to, find out what the answer is. And human beings have been asking this question for thousands of years. Philosophers guessed at it, alchemists experimented, chemists found patterns, and over the last 2 centuries, physicists started finding actual answers. And I think the answers are stranger and more beautiful than anyone could have guessed. And I think the way that I think about understanding physics, it's like watching a TV show that you really, really end up enjoying. And you kind of wish that you could erase your memory just to be able to rewatch your favorite show or what has become your favorite show once again, and to be able to relive for the first time the joy and the wonder and just the absolute like uh the whimsy of like figuring out all of this knowledge is around us. And I think this is how I think of physics. Sometimes I'm jealous of people learning this for the first time because it means I know what that feels like, that you really understand something and it is so beautiful and strange, and it kind of does this thing in your brain where it clicks and it makes sense and it's intuitive, like your brain has always understood how it worked. It just needed you to put the words or like formulate the words together. And this is really what this episode is about. It's about what this is, like everything around you, who you are, what you're made of, what the universe is made of, and how it works. The universe that we live in is just absolutely beautiful. And this is why I'm calling it episode 0, because it's just laying the groundwork for everything that is going to be coming next. So sorry, going back on track. So what is matter? What is it made of? What does particle physics even mean? And why does any of this matter? Let's leave aside the equations, the complicated vocabulary, and let's focus on the ideas. So let's look at a wooden table. It's the most ordinary thing that I could really think of. And you can see the table, you can touch it, it has color, it has texture, it has weight, and it feels completely real and completely solid. And so imagine your eyes had the ability to zoom in far enough into the table that and you can see smaller and smaller scales. So first you would see a grain of wood, then you would see the individual fibers of wood, then you would see the cells that make up those fibers, and then smaller still, the molecules, and then chains of atoms bonded together, and then the chemical structure of cellulose. Then you would see the atoms themselves. And if you're listening to this, you should look up what the structure of an atom looks like, because I think having a diagram in front of you is just all that more helpful. So an atom is almost incomprehensibly small. A single human hair is roughly 1,000,000 atoms wide. And I think, you can grab at your hair and you can see how small, how thin a single human hair is. Now imagine a million atoms making up the width of your human hair. And if you blow up an atom to the size of a football stadium, the nucleus at its center, the brain of the atom, would be about the size of a marble sitting on the 50-yard line. So, you know how big a football field is. So if an atom was the size of a football field, then the nucleus would still be the size of a marble. Do you understand how massive the difference in scale is? And this is because the rest of the atom is essentially just empty space. And the part of the atom that is actually stuffed is very small compared to the size of the atom itself. And this is the first strange thing. So, we go back to our wooden table. It feels really solid. It's almost entirely nothing, though. And what makes it feel solid, what makes it feel like anything at all, really, is not the matter inside of it. It's the forces between the particles. But we'll come to those forces later. For now, atoms. Everything you can see, touch, taste, or smell is made up of atoms. Your body, the air, the oceans, the stars, all are made up of atoms. And there are about 19 naturally occurring types of atoms. And these are what the periodic table catalogs. So here I'm talking about hydrogen, carbon, oxygen, iron, gold. Each one is a different species of atom with different properties, different behaviors, and different roles in the chemistry of the universe. And okay, so going further still into atoms, they are actually not the smallest thing. They are not the bottom. And so when scientists first figured out that atoms have internal structure, they were genuinely shocked, which I think is not shocking. And so the word atom comes from the Greek for something that is uncuttable. So you can't cut it. It's the smallest thing possible. It is very fundamental. And the whole point was supposed to be that you could really not go smaller than an atom. But it turns out you can. And every atom has a nucleus at its center. The nucleus contains two types of particles, okay? Protons and neutrons. And surrounding the nucleus in a kind of fuzzy cloud are electrons. So protons, neutrons, electrons. Protons carry a positive electric charge. Electrons carry a negative electric charge. And neutrons carry no charge at all. They are electrically neutral, which is where their name comes from. So the number of protons, the number of positively charged particles you have in the nucleus is what determines which element you have. So, for example, if you have one proton, that is hydrogen. If you have 6 protons, that's carbon. If you have 8 protons, that's oxygen. 26 protons is iron, and so on. The proton count is like the identity of the atom. If you change the proton count, then you have a different element entirely. And so electrons are what make up chemistry. When atoms bond together to form molecules, for example, when hydrogen and oxygen combine to make water, when carbon chains link up to form the molecules of life, it is electrons doing all the work. They are the, I guess you can say, social layer of the atom. They're how atoms talk to each other. This is due to electrons. So protons give you the identity, and electrons are the social. They're how atoms talk. So I think now you have a sort of a small picture of what physics looks like. You know that atoms are made up of protons, neutrons, and electrons, and we are still not at the bottom. We go further still. So in the mid-20th century, physicists started smashing protons and neutrons together at very high speed. And they kind of just sat there and watched what came out. And they found out that protons and neutrons are not fundamental. They are not the smallest things that we can have. Even protons and neutrons, these positive and neutrally charged particles, have an internal structure. They're made up of something. And these things that they're made up of are quarks. Quarks. A proton is made up of 3 quarks. A neutron is made up of also 3 quarks. And quarks are held together by a force, a very powerful force called the strong nuclear force. And I think the name is kind of intuitive. You have a really powerful force, it's a strong force. And so it is called the strong force, the strong nuclear force. So as the name suggests, it is strong and it's what keeps quarks together. And it is strong enough to overcome the fact that positively charged protons in a nucleus are all trying to repel each other. And so quarks, these very fundamental, very, this very small, things that make up protons and neutrons also have types. And so physicists, with a little mix of whimsy, named them up, down, charm, strange, top, and bottom. So those are 6 types: up and down, charm, and strange, top and bottom. And a proton is made up of 2 up quarks and 1 down quark, and a neutron is made up of 2 down quarks and 1 up quarks. And here's something important about quarks. You'll never be able to find one on its own. What does that mean? It means quarks are always bound together. The strong force that holds them is strange. It's unlike gravity or electricity, which gets weaker as you move objects away from each other. The strong force between quarks stays strong no matter how far you try to pull them apart. And it is like trying to separate 2 ends of a rubber band. The further you pull, the harder it pulls back. Eventually, if you put in enough energy, this rubber band, the strong force, snaps. And instead of freeing the quarks, the energy of the snap creates new quarks to replace the ones you're trying to separate. So nature apparently does not allow quarks to get lonely. Forces are what make matter do anything. Without forces, particles would just sit there, inert, not really interacting, not really forming atoms or molecules or stars or people. And so there are 4 fundamental forces in nature. 4. And everything that has ever happened in the physical universe, every chemical reaction, every heartbeat, every supernova, every thought you have ever had is a consequence of these 4 forces operating on particles. The first is gravity, and I think we all know this one. It pulls masses together. It keeps you on the ground. It keeps the Earth orbiting the sun. It shapes the large-scale structure of the universe. And gravity is the weakest of the 4 forces by a huge margin. Much, much, much weaker than everything else. And it has an unlimited range though, and it always attracts, which is why it dominates at large scales. And so the second force is electromagnetism, and this governs the behavior of charged particles. It is the force between electrons and protons, the force that holds atoms together, and the force that makes chemistry happen. Electromagnetism. It is also the force responsible for light, radio waves, X-rays, and everything else on the electromagnetic spectrum. This is the force we will be spending the most time with across this series. The third is the strong nuclear force, which I already talked about before, the strong force. The strong force is a strong force. It is the one that holds quarks together inside protons and neutrons. It's strong enough to hold them together, even though protons are trying to repel. And when I say hold them together, I mean it's trying to hold protons and neutrons together inside of the nucleus. And the strong nuclear force is extremely powerful at very short ranges. And it is basically 0 at longer ones. So gravity is strongest at large scales, and the strong nuclear force is strongest at short scales. Finally, we have the 4th force, which is the weak nuclear force. And this weak nuclear force governs a certain type of radioactive decay. Radioactive decay is the process where one type of particle becomes another type of particle. As the name suggests, the weak nuclear force is in fact weak, It is short range, and it plays a crucial role in nuclear physics and in the processes that powers stars. So 4 forces. That is the complete list. And as far as we currently know, every push and pull in the universe traces back to one of these 4. Now, so if you pulled up the picture of an atom before, I want you to pull up a picture of the standard model of physics, the particle zoo. And try not to get dizzy when we talk about this, because we will talk about protons and neutrons and electrons and quarks. And these are the particles that make up ordinary matter, but they are, in fact, not the only particles in nature, as the standard model of physics shows. When physicists started building particle accelerators, which we'll talk about this more, but they're basically machines that smash particles together at really high speeds. They found that collisions could produce particles that do not exist in stable matter. Particles that live for fractions of a second before decaying into something else. The particles basically that have a very short lifespan. They exist for a very short amount of time and then they become something else. Particles that seem to carry forces rather than matter. This period, which was roughly from the 1930s through to the 70s, became known informally as the particle zoo. New particles just kept showing up faster than anyone could make sense of them. And it was, by many accounts, deeply confusing. But turns out that with that confusion came order. Physicists eventually organized all known particles into a framework called the Standard Model of Physics, and it is one of the most successful scientific theories ever constructed, tested to extraordinary precision, and confirmed by decades of work. The Standard Model divides particles into 2 broad families. The first family is matter particles. These are the building blocks of matter, and these include quarks, and a family of particles called leptons. Leptons include electrons and the ghostly, almost massless particles called neutrinos, which are just my absolute favorite. And there's a whole episode on neutrinos in this podcast, and they're crazy particles. Just kind of do whatever they kind of just do whatever they want, which makes them super interesting. So, So there's the family of matter particles, the building blocks, which are quarks and leptons. And leptons are electrons and neutrinos. And there are 6 quarks and 6 leptons. So we said before 6 quarks are, let me see if I remember them, up, down, strange, charm, and 2 others that I cannot remember. And there are 6 leptons. And they're organized into what we call 3 generations that mirror each other in structure, but they increase in mass. So there's 3 generations. As you move from one generation to the other, their mass increases. And the second family is force-carrying particles. So first we had matter-carrying particles, now we have force-carrying particles, and these are messengers. In quantum physics, forces are not transmitted by invisible strings. They are transmitted by particles. The electromagnetic force is carried by photons, the strong force is carried by particles called gluons, and the weak force is carried by particles called W and Z. And there's one more, which is the Higgs boson, and it is not quite a force carrier and not quite a matter particle. Its job is to give other particles their mass. Its discovery in 2012 at the Large Hadron Collider at CERN was one of the landmark moments in modern physics. And so that is the standard model: 17 particles, 6 quarks, 6 leptons, 4 force carriers, and the Higgs boson. That is the list of ingredients the universe uses to build everything. So, here's what we do not know. Even though the standard model is extraordinarily successful and it is, however, obviously incomplete, it doesn't include gravity. Because gravity, despite it being the most familiar force in everyday life, has resisted every attempt to fit into the same framework as the other 3 forces. There's no confirmed quantum theory of gravity. That is a major open problem. It does not explain dark matter, which also has its own episode on this podcast, and observations of galaxies in the large-scale structure of the universe suggests that about 85% of all matter in the universe is something we cannot see. something that does not interact electromagnetically. We do not know what it is, and none of the particles in the standard model seem to account for it. For example, it does not explain why there is more matter than antimatter. And okay, so every particle has an antimatter counterpart, a mirror version with opposite charge. So, for example, electrons have positrons, which share the exact same mass and spin as a standard electron, but they carry a positive electrical charge instead of a negative. And so when matter and antimatter meet, if an electron and a positron meet, they annihilate each other. They cancel each other out. They kill each other. And in the early universe, matter and antimatter should have been created in equal amounts, and they should have destroyed each other completely, which would have left nothing behind. There would have been no universe, no you and me, no planets, no stars, no nothing. But here we are. Something broke that symmetry, and we do not fully understand what, because there's actually more matter than antimatter, which stopped them from canceling each other out, which allowed us to exist. And so these are not minor footnotes. They are enormous open questions sitting at the center of physics. And this is exactly why particle accelerators exist, why plasma physics is exciting, and why the work we are going to be talking about throughout the series matters. The standard model is a triumph, and it is a starting point. So here we are. Everything you have ever seen or touched is made up of atoms, and atoms are made up of protons, neutrons, and electrons, and protons and neutrons are made up of quarks. And quarks and electrons are, as far as we currently know, fundamental. They do not seem to be made up of anything smaller. And forces are what hold all of this together and make it interact. Gravity, electromagnetism, the strong force, the weak force. Each force has its own carrier particles. The full catalog of matter particles and force carriers is what we call the standard model. And underneath all of this, the thing that we will spend the rest of the series exploring are fields, invisible structures that permeate all of space, whose vibrations are what we call particles and whose interactions are what we call forces. And so next, we are pulling on that thread. We'll talk about electricity, magnetism, and the man who showed they were basically the same thing, and accidentally discovered the nature of light in the process. And the deeper you go, the stranger it gets. Until next time,